Use a table of values to sketch a graph of f of x equals the square root of x minus 2 and g of x equals the square root of x minus 2. First, we'll start with f. We want to pick values of x. Ideally, where taking the square root is fairly simple. So we can pick perfect squares, 0, 1, 4, 9, etc. We could pick a number that's not a perfect square, like 7. That'll give us a decimal, but we can handle it. And we're not going to pick any negative numbers, because if we pick a negative number, we end up with something that's undefined. So let's evaluate these square roots. When x is 0, the square root of 0 is 0, and 0 minus 2 gives us negative 2. When x is 1, the square root of 1 is 1, and 1 minus 2 is negative 1. When x is 4, the square root of 4 is 2, and 2 minus 2 is 0. When x is 9, the square root of 9 is 3, 3 minus 2 is 1. And when x is 7, the square root of 7 is approximately 2.6, and 2.6 minus 2 is 0.6. This is an approximation, but that should be good enough for our graph, which we can draw now. We've got our points 0, negative 2, 1, negative 1, 4, 0, 9, 1, 7, about 0.6. And if we look at this, this looks very similar to the graph of the square root of x, only instead of starting at the origin and moving up and to the right, we're starting 2 units lower. And that's because 2 was being subtracted in this function. So we can connect these dots. We know this is going to be the end point. It can't go any further to the left because the square root of a negative number is undefined. And so this is the graph of the function f of x equals the square root of x minus 2. Let's look at g now. Here, we want to pick values of x, specifically so that x minus 2 is a perfect square. Now, if you find that to be a little bit abstract or challenging, you can pick any values of x that you like, and you can always plug them in to get your y values. However, let's try to be a little bit smart about this. We know that the perfect squares are 0, 1, 4, and 9, and of course more of them, but those are the ones that fit within our x-axis in the template. So if we want the inside to be 0, for example, then a good x value would be 2, because 2 minus 2 is 0. So if we let x be 2, that's going to make the inside 0, which is a perfect square. And in fact, we can take the square root of 0. The square root of 0 is 0. So when x is 2, g of x is 0. Now the next perfect square is 1. If we wanted to make this inside 1, then x would have to be 3, because 3 minus 2 gives us 1. So that gives us an x value of 3. But then if we evaluate this, 3 minus 1 is 1, and the square root of 1 is 1. So that gives us a y value of 1. I know I'm doing this a little bit differently than I usually do. Usually I pick the x values, and then we plug them in to get the y values. You can still do this problem that way, but I want to do it a little bit different to see if you can think about it a little bit differently. I want to challenge you just a little bit. All right, let's continue. The next perfect square is 4, so if the inside was equal to 4, that would work out nicely. To make x minus 2 equal to 4, x has to be 6, because then 6 minus 2 gives us 4, And when we take the when we take the square root of 4, we end up with 2 for our output. All right, we know that the next perfect square is 9. To make this 9, x would have to be 11, because 11 minus 2 gives us 9. And then when we take the square root of 9, we end up with 3. So now we've got 4 nice values that give us 4 points that we can plot on the xy plane. All right, we've got the point 2, 0, 3, 1, 6, 2, and 11, 3. This looks very similar to the square root graphs that we've seen before, only this one is moved to the right 2 units, unlike the last one, which was moved down 2 units. And we know that this is going to be the end point, because if x is less than 2, then x minus 2 is going to be negative, and we can't take the square root of a negative. So this is the end point, and we're going to move up and to the right from there. It's maybe not as pretty of a graph as the last one. I didn't do quite as good of a job of connecting the dots in a beautiful curve, but hopefully you get the point, and you can see that this is the graph of g of x equals the square root of x minus 2. Again, we're seeing that if we're adding or subtracting a constant, that takes the original graph and moves it, in this case downward, in this case to the right, and in the last examples we saw where it moved it up and to the left. Again, this is something that we're going to be exploring more in depth pretty soon, how changing the equation for a function affects what the graph looks like.